I'm Queenie J. Salion.
I am Rachel Mikagapi.
I am Mitch Angelo Lecera Benting.
And I am Kent Dave Lauren Ardoblas.
Okay guys, I just finished watching that video about polar coordinates. It was actually really cool. I think I get the difference between rectangular XY and polar R theta coordinates now.
Yeah, same. Rectangular coordinates use the x and y axis, while polar coordinates use the radius and angle from positive x-axis. So instead of moving horizontally and vertically, we rotate and then move outward.
Exactly. So a polar coordinate is written as r and theta, where r is the distance from the origin and theta is the angle in degrees or radians.
Right, and they mentioned that positive angles are measured counterclockwise while negative angles go clockwise from the positive x-axis.
Okay, so let's try an example together. Say we want to plot the point 3 and 45 degrees. What would we do?
We draw concentric circles, one with radius 1, one with 2, and one with 3.
And then, since the angle is 45 degree, we draw a ray that starts at the origin and goes out at 45 degree. That ray intersects the circle of radius 3, so the point is located there.
Perfect, just like that 45 degrees is in the first quadrant between 0 degrees and 90 degrees. So we know it's up and to the right.
What about something in radians like 2 and 3 pi over 4?
Let's convert it to degrees. So 3 pi over 4 times 180 degrees over 5 is equal to 135 degrees.
35 degrees is in quadrant 2, between 90 degrees and 180 degrees. So we go out to radius 2 along that 135 degrees line.
That point would land between the second and third circles, right at the second one.
Here, this is our plot for 2 and 135 degrees. So cool how the direction changes based on theta.
But the part that messed with my head a bit is when r is negative. Like say we want to plot negative 2 and 60 degrees. How do we deal with that?
The part is tricky. Remember what the video said, when r is negative, we move in the opposite direction of theta.
So, for negative 2 and 60 degrees, we first plot 2 and 60 degrees, which would be in quadrant 1. But since r is negative, we go to the opposite side of that ray, adding 180 degrees to theta.
So 60 degrees plus 180 degrees equals 240 degrees. That's where the point negative 2 and 60 degrees ends up along the 240 degrees direction, radius 2.
Let's try another one. Negative 3 and 120 degrees. First, plot 3 and 120 degrees, which lands in quadrant 2.
Then for negative 3 and 120 degree, we go 180 degree. More, 120 degree plus 180 degree is equal to 300 degree. So the point is at the radius 3 along 300 degree, which is in quadrant 4.
And the video showed how to represent the same point in different ways. So, negative 3 and 120 degrees is the same as 3 and negative 60 degrees, negative 3 and 120 degrees, and 3 and 300 degrees.
It's like a secret identity. One point can have multiple polar representations.
So to summarize, 1, r and theta, 2, r, theta, and negative 360 degrees, 3, negative r and theta plus 180 degrees, 4, negative r and theta minus 180 degrees. As long as the new angle ends up pointing to the same location.
That with 2 and 30 degrees, what are the 3 other polar coordinates for the same point?
Alright, first one, 2 and 30 degrees, which is the original. And the second one, same are theta minus 360 degrees implies to 2 and negative 330 degrees. Third one, negative r theta plus 180 degrees implies to negative 2 and 210 degrees. And the fourth one is negative r theta minus 180 degrees implies to negative 2 and negative 150 degrees.
Boom! 4 versions of the same point.
Let's plot all four on the same polar grid to visualize that they land at the same terminal point. We'll see that they're just approaching the point from different paths.
What I really liked was how flexible polar coordinates are when you're representing angles, like could use 360 degrees and negative 300 degrees, or even 2 pi and still get the same direction.
True, and sometimes it's better to use radians in trigonometric functions, especially for calculating arc lengths or area of sectors.
That reminds me, polar coordinates are super useful in real-life applications like navigation, robotics, electrical engineering, and even modeling spiral galaxies.
Right. Anything with circular motion or radial symmetry makes more sense in polar form, like describing the location of a planet in orbit.
So if someone gives you r and theta and asks for rectangular form x and y, we can convert using x equals r times cosine theta and y equals r times sine theta.
From rectangular back to polar, r equals square root of x squared plus y squared. Theta equals inverse of tan y over x. But we have to be careful about which quadrant we're in.
Definitely, because inverse tangent doesn't always tell the whole story. Sometimes we need to adjust theta by adding 180 degrees or subtracting based on the quadrant.
So let's try this one. Convert 3 and 45 degrees to rectangular.
So in this problem, we'll use x equals 3 times cosine 45 degrees equals 3 times square root of 2 over 2, and that is approximately 2.12. And second one is y equals 3 times sine 45 degrees equals 3 times square root of 2 over 2. So that is approximately 2.12. So the two is approximately 2.12 and 2.12.
Nice! That's a perfect example of how polar and rectangular coordinates relate.
Okay, last challenge. Find all four polar coordinates equivalent to 2 and negative 45 degrees, with theta between negative 360 degrees and 360 degrees.
So let's go. Number 1 is 2 and negative 45 degrees. Number 2, 2 and 315 degrees implies since negative 45 degrees plus 360 degrees. Number 3, negative 2 and 135 degrees implies add 180 degrees to angle. And the last one is negative 2 and negative 225 degrees implies subtract 180 degrees from negative 45 degrees.
Boom! Got him!
Awesome work, everyone! I feel like we really get this now. Next time, let's try plotting polar equations like cardioids and spirals.
Yes, and maybe even converting equations between polar and rectangular forms.
Agreed. Today was all about understanding the coordinate system. I'm actually excited for what's next.